so your head's in the thing, so you can make sure you're in the frame. You're taller than me, so you can adjust as needed. The mouse is like, you should be able to just drag it over here. Like it should work like intuitively, because I rearranged the settings for it.
Oh, that's nice. Okay.
Yeah, so if you get stuck, let me know. Otherwise, I'm gonna camp over here.
Okay. Hi everyone. Hi Roomers. Hi Zoomers. Sorry, I'm used to looking at the screen. So starting with the formative assessment, the first question, looking at the model notation for a GLM with a single predictor of an outcome, can anyone tell me what is or how to describe the beta 0? Is this working? Nope. I was gonna point, yeah.
There you go.
Beta 0, this.
Like that.
Yeah.
It's the intercept, so it's the expected value of y sub I and all values for x sub I are 0.
Yeah, I would add the clarification that Lisa always adds, that it is a fixed intercept because it's constant for everyone. But yes, so it is the predicted outcome for the y sub I when all of the predictors, in this case the x sub I, is 0. What about this beta 1? Does anyone know what it's called, what it does?
It's a slope.
A slope? Yes.
It's a fixed slope
Yes, fixed slope.
for whatever x of one variable is.
Mm-hmm. So
Or
could
sub
you
I.
put in a sentence how that impacts the other variables in the model, specifically the outcome?
It increases or decreases based upon your x value. I mean, one increase of 1x will make it go up or down, whatever base of 1 is.
Mm-hmm. So for 1 unit increase in x, there's going to be the beta 1 increase in the y sub I. And then the last one, the e sub I. Anyone know what that one's called? Everyone coming in now.
I think it's the residual representing the difference between the
Yeah. So like it has the little sub I. So for each person, the predicted outcome, you're seeing like what each person's difference is from that predicted outcome. So great. And then you're next. So trading.
So now you know I have questions 2 and 3. So for question 2, the same GLM with variables y equals enthusiasm for school and x equals weekly hours of Nintendo played. Interpret each estimate in the following solution. Can anyone tell me what 80 represents? Zoomers, roomers, anybody? The intercept. Yes. Can anyone tell me what 2 represents?
-2
Negative
represents the slope.
No.
Yes, exactly. What is xi?
That's the value you're trying
Enthusiasm
to
for
predict.
school.
Yes. And it is a... Yes. And it's a variable. What is e sub I?
It's which,
Yes. So
it's the I point.
exactly. So in walking through this kind of step by step, 80 represents when we cancel out the hours played for Nintendo. So when an individual plays 0 hours of Nintendo, their enthusiasm for school value is expected to be 80. Some of you asked on the homework what that actually means. We talked about it and we kind of came to the solution that it's basically a 0 to 100 scale. If we just pretend it's a 0 to 100 scale, it's a feeling thermometer.
That's a thing.
And I'm sure it is. Pretend you're in kindergarten and you have a feeling thermometer when you walk in. Your enthusiasm for school, 0 to 100. If you played 0 hours of Nintendo, your expected value for your enthusiasm for school is going to be 80, right? 80 out of 100, which is not bad. However, let's say you played 10 hours of Nintendo over the weekend or however this is measured. Now, your expected enthusiasm for school is going to be 60. It's going to go down, right? It's going to go down by 2 points for every hour you play of Nintendo. And that's what we're looking at here. You all did a great job with this. The one note that I would make is that a few of you kind of went above and beyond with this E, with the residual, and did a nice explanation of the residual is anything that's left over, right? So when we take our line, we have our mean, right? Our empty model is that straight line that we've talked about that Lisa's used her teacher pointer for, right? And then we have that -2, and we're trying to fit it to the data a little bit more, right? So we're slanting this line downwards. And our E is going to be that distance between our predicted value for any one individual, any one student in this data set, between our predicted and our observed value. Does that make sense? Does anybody have any questions with the residual, the slope?
All the reasons why people differ in enthusiasm besides Nintendo.
Yes, exactly. It could be if there's different classes offered. It could be if they had homework to do, like hours of homework they spent. That could affect enthusiasm. Anything that we might expect to affect enthusiasm or be related to enthusiasm. For question 3, if X equals weekly hours of Nintendo were centered at 10 instead, which estimate in this solution would change and which would stay the same? So I have a couple questions with this alongside the actual question. So let's start with what would change. What would change about this y sub I equals 80 minus 2 times x sub I?
Intercept will change.
Yes, the intercept would change. What would stay the same?
Slope
And?
Slope is same.
and the residual.
And
For
the
that
residual.
point.
Yes, exactly. So the intercept would change, and the slope and the residual would stay the same. Now, my questions are, can anyone tell me why that is?
Because baseline are not change. Baseline change. A starting point change. But the relationship between variables not change.
Thank you. Yes, that is spot on. So our relationship doesn't change. For every hour increase that you play Nintendo, your relationship with your enthusiasm for school is still going down by 2 points for every hour increase. But your starting point, our starting point and our baseline for that intercept is changing. So we can interpret it in a different way, right? So for example, if we don't have anybody in our data set that played 0 hours of Nintendo, it might not be all that interpretable because we don't have that in our data. But if our minimum or our maximum or our mean, say, is 10, we might want to center on that 10 to make it more interpretable so that when we zero out our variable of hours played, we're now sitting at the mean or the minimum or the maximum or whatever it may be, which is 10. My second question is, who here, if you, in this question, decided to interpret what the new intercept would be, who here thinks it would be 100? Mm-hmm.
When we center it over, because I looked at the other graph and when we shift things over, I was like, since it's negative, it might be up a little bit.
Right, it might be
But
up a
I
little
don't
bit.
think that's right. I think it's 60.
Okay, who here thinks it's 60?
Or maybe not, was I right? That's what
It's 60, because that's what was on my note.
Yeah, I did give them the answer, and they've looked at the quiz scores.
Okay,
they got the
okay,
answer,
okay.
so.
All right, so you have the answer. All right, well, thanks for ruining my fun.
I know.
Okay. Well, for those of you, as Lisa talked about in last class, some people are visual learners, some people are the word learners. To get a little jargony, for people who got 100, what you had done is you were interpreting this as simply putting in the x sub I minus 10 and plugging in 0 for that x sub I, so that your equation read 80 minus 2 times minus 10, which would then invert to 80 plus 20, which would give you 100, right? For those of you that got 60, you correctly identified that in order to get the new intercept, we need to plug in what the value that we're centering at for x sub I. So it would be 80 minus 2 times 10, which would be 80 minus 20, which would be 60. Okay, that's the jargony talk. The visual talk is simply like this.
Can't draw,
Can't draw?
no.
People,
can't
they can't see. That's okay. I did this for both my arms too. Okay, so you have
Did I
this,
talk with
right?
my hands?
Yes, you have this, okay, and then you have Lisa's talking point, right? And our slope is downwards shifting, right? It goes downwards, okay? It's impossible for us, if we shift 10 points to the left, because we're subtracting, so we're shifting to the left. It's impossible for us to then have a higher value for the intercept, right? Because we can't have 100, because if we're going down for every hour increase in Nintendo play, and we subtract by 2 for every hour increase, and if we move that 10 points to the left, our intercept is going to be now at 60 instead of 80. We're not going this way, we're going this way, right? I know this may be confusing for those, but on Zoom, it
You want to
makes
draw?
much
I
more
can get
sense.
paint out for you.
For those of you that do understand in the room, maybe the paint would work.
No, that's why I get paint out, because you can't draw on the board and have it captured. But if you draw in there, then you can see it.
Look at that.
Yeah, I know.
I've used notebooks
Yeah,
before,
same.
pieces of paper. So,
Excellent.
There's your axes.
There it is. Okay, thank you. Okay. So we're going down. Wow, this is like looking without context. Okay.
so which line is that? Is that before or after you shift? That you just drew?
So this is before,
Okay.
right? So right here, this intercept is 80, right? Right now. Look at that blurry -5 astigmatism. Oh, nice. Oh, that's all right. Okay, but if we're subtracting 10, we're not going to be moving to the right, right? We're going to be moving to the left. Same thing that we did in the example, except we had a positive slope. So that's why the intercept increased. Because we're still moving to the left, but because it was a positive slope, that intercept is now going to increase. If we're moving this way, right, and our slope is still the same, this is our new intercept, which is going to be 60. I would pretend to draw that. There we go. 60. Does that make sense? I'm seeing some nods, some head nods. Anybody have any questions? Robin, I'm seeing a head nod. You're lost. Anything in particular that you're lost about? And it's okay if you say
Wait,
everything.
so what does 60 mean then? So like we've gone from 80 to 60, now to find 60, what does 60 mean?
It's a great question. So 80, if we remember from the original equation, right, the original formula, 80 represented the enthusiasm for school when somebody didn't play any Nintendo. Do you remember that? Okay. So when we have, for example, our data set doesn't have anyone that played 0 hours of Nintendo, let's say the mean was 10, right? So when we subtract 10 from every data point and we're shifting over by 10 points to the left, that is supposed to be a 10. Now, we say for an individual who played 10 hours or played the mean of Nintendo hours, their enthusiasm for school is now 60. It would be the same interpretation if from the original formula we simply plugged in 10, right? And so that's how you get that new intercept. The only reason we're doing this is to make the intercept interpretable. In practice, it can be as little as not important at all to the most important thing because you're interested in the intercept. And right now we're interested in the intercept. So that's why we recenter on the mean of x. Let's pretend it's the mean, right, for consistency. So now we're saying when somebody plays the mean hours of Nintendo, their expected enthusiasm is 60 on a scale of 0 to 100. Does that make a little more sense? Okay, and that slope is still the exact same. If we were to say somebody played negative, that minus 10 is that 0 hours on the centered, we'd still get 80. But we're just recentering to make it a little bit more interpretable for our liking, for however we want to do it. Anybody else have any questions on that one? Okay. All right. Put your glasses back on. That is, yeah, that's
Whoa.
something. That's something.
That's
all right.
Paint is the first program I learned how to use on a computer. I was like 8 years old and playing with
Heck
Paint
yeah.
on Windows 95.
Oh yeah.
Windows 95.
That would have been like Windows 89, whatever the precursor was. Yeah. Yeah, it's a thing.
Okay, so moving on to the last question. So talking about standard deviation and standard error. can anyone tell me what standard deviation typically refers to?
How far the individual is off from the sample mean.
And would you say that it's always the sample mean, or could it be a different kind of mean? It's okay if you don't know. It's a leading question.
Yeah.
So when you have like a model, like the previous one we saw, and we have a predicted mean, you can also have the standard deviation of the predicted mean. So similar to how you're saying like the person from the sample grand mean, but in this case it could also be from the predicted mean. So just person from mean.
Yeah. It's like, is it the standard deviation of y, or is it the standard deviation of e that's left over from y? And that's the difference.
Okay.
Yeah.
And then going into the standard error, can you tell me what that one refers to? If the standard deviation refers to people and the means.
Variation across samples.
Yes, variation across samples, that's great. And so if you're getting a standard error, what estimate can you get that for?
Sample value. It's like slope.
Yeah, slope. Any other guesses? Do you think it's just a slope, or could there be other things that it could be?
There could be other things.
Yeah. So it's for any of the fixed effects from the model that you can get the standard error. So the slope, the intercept, like the predicted, the mean, if you're using an empty model. So then how does the standard error and standard deviation relate to each other? Or how are they, what do they have in common? Not in common, to relate to each other's question.
Both measure inconsistency.
Yeah, you think of like how Lisa talked about like the width.
Yeah.
Like they both measure width. It's just like what you're comparing to your reference values. Yeah.
Isn't one like one's like wrongness with, say, the variable or the person, and one is the wrongness like with among samples? Is
Yeah.
that, okay.
Yeah, it's like the precision was the word that Lisa used a lot, relating to the standard error. So how precise you're getting that estimate, or how wrong if you're thinking the opposite way from like the slope or the intercept or the mean. Whereas the standard deviation is how, is the average person from the mean. Yes?
And then if the population increases, does both standard deviation and standard error decrease?
So if you have more people, and then,
They get narrower.
and so how, and if the standard deviation, do you remember, can I pull up the,
Yes, lecture 2 is up if you want to.
where? That's the question. I,
Yeah, tell me what you want and I'll find it.
if I look, this photo. Yeah.
$17?
Yes.
That one?
Yeah. Okay. So yeah, as you get more people, see this one's like 15, the larger in here. What's happening with the standard deviation as we get more people? Yeah. So then if you're getting how that affects the standard error, what were you saying before? Is it?
I said standard deviation and standard error both decrease.
Yeah, so if you're having like smaller variability, then you're going to have more precision about where your estimate is. Because the standard error is often using the standard deviation of a variable in the model, or the variance of it, which is the variance and standard deviation are related to each other. So you're getting that if it's closer together, it's easier to have more precision, because you're like, okay, this is a lot easier to tell than like this one's a lot wider. And check if I'm missing anything. No? Any last questions?
I have a question going back to you were saying with the standard deviation can be the actual deviation or like the predicted deviation.
Mm-hmm.
So obviously, well, the null hypothesis is saying there's going to be no change. So would that be the alternative hypothesis? I mean, I guess like how specific do you get in your alternative? Like, are you saying I expect this to be the standard deviation, or is it more just like I expect there to be a change? I mean, like, I don't know, how specific do we get?
I'm like, do you want me to answer?
Yes.
Oh, yeah. I'm just,
Sorry.
no, you're good. So when we're talking about like standard deviation in general, we're just talking about like the spread. So if we're looking at like the predictive model, we're looking at the spread of like the error. So we're not really making the hypothesis testing about that. We're just like assessing, okay, how well did this model predict? Is the variation like really large to do like a really bad job, or is it like smaller? And so that's what you're really looking at. Any other questions? Okay.
You giving them applause? That's
Why not?
nice. Yeah, it can be a little intimidating to come and stand up here, am I right?
Trying to figure out your screens.
Yeah, exactly. So yes, so this one ended up being, I think, not very well worded on my part, but the big picture, right? We talk about standard deviation, like, and it's sort of assumed that's about y. Well, that's the starting point for the empty model, right? E is like all the offnesses that you have from y, like the difference between the means. And as you refine what y is supposed to be by adding predictors, then your e's should shrink. So in building your standard error, the less wrong you are, the better your standard error should be. The more people you have, the better your standard error should be. So they are tied together. If you have a variable that starts out with a variance of 100, then the standard errors that are come out of that model are necessarily going to be different than a variable that starts out with a variance of 10. So that the model understands the scale of the variables already. What's relevant to this is as we include more predictors, if the predictors are doing a good job, if they do have a relationship, the e's keep getting smaller and smaller and smaller, so do the standard errors of everything in your model. We have more precision when there's less unknown information that's remaining in the system. And in terms of the null hypothesis thing, yeah, the alternative hypothesis is not 0. Could be high, could be low, because we're doing 2 tail tests. So not 0 is all we got for now. Okay. Any other questions or things that you want to talk about with respect to the formative assessments? Yeah, go ahead.
So I'm looking at the PowerPoint again, and so a two-tailed test, is that just absolute value? Like, partially?
Yes.
I was like,
Yeah.
I didn't think about it that way.
Yeah, that's why on the output, let me find an example. It's written like this. P exceeds the absolute value. P if the absolute value of t is exceeded, I think is what that actually means. It could be better labeled, but yeah, it's a two-tailed hypothesis test. And essentially, if you wanted a one-tailed, you would take it and double it. So.
And I have a question.
Or cut it in half, excuse me, I'm going the wrong way. Yes.
Okay. So some of these, the results from the R, which shows the P is a 2e minus 16.
Yes.
But which is equal 0, but I don't know what is the interpretation of. Yes, this one.
That is
Scientific
scientific notation.
So what is exactly this mean?
What it would mean is, let me see if I can put it in here.
2 times 10 to the negative 16th.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 2. Is that right?
Yes.
Thank you. It's been a minute since I had any formal math classes, but that's what that means. And so that is actually controlled in the top of the R syntax file. There's global options for what the display looks like. You can say how many digits you want before it switches to scientific notation. So I think mine says 9 or something, but you can put it as like 1,000,000, and then this is what will show up on your output, is like 1,000,000 zeros printing across. Yeah, and the minus sign means it's going this way. A plus sign would mean scientific notation the other way. Like all the zeros would be after the 2, so that would be like that way instead. There, we'll get rid of that. So future me is not confused. All right, other questions? We're good? All right, can we talk about homework briefly?
Sure.
Yes.
Yeah. So homework 2 is available to you. It is due next Wednesday. So if you're like, yeah, I haven't started that yet, that's fine. I just wanted to demonstrate a couple of things to make sure that we're all on the same page with respect to what to expect. So this landing page, when you log in, I update things manually that go into these point totals. So if I haven't downloaded the data and processed it yet, your point totals won't be updated, but you can always log into your specific assignments and see your scores that you were earned. So note that it tells you how many homework points you have out of whatever is possible. So we have 12 currently from homework 1. Homework 2 is in progress. It tells you how many quiz points you get. So out of 4 possible, if you've done both of them, then you get all 4 points. And then I keep track of bonuses. And so like my current grade is 4.46% because I'm not doing any of the work in here, but you can see where you currently stand. And because the bonus points are factoring in heavily so far, they contribute to the numerator, but not the denominator out of possible. Like most of you have like 110% or something. So I feel like psychologically that's a better place to start from, right? You know, you're doing better than perfect as opposed to working your way up from 0. Inside homework 2, the structure of this is just like last time. Here's your data set that you will need to do the problem. Each of you has your own data set. There are starter syntax files in your program of choice. So for this, for instance, here's the R1. This is this option right here, SciPen. That's the one for scientific notation. So you can set that to whatever number you'd like. Also, R star shows significant stars. I don't like that kind of clutter in my output, so I turn it off. But if you like to have the stars, you can turn it back on. And this is also the number of significant digits. It's not significant, number of digits printed, I would say. And that includes both the whole number part and the decimal part. And it needs to be 7 to get enough digits for the homework system. So Erica figured that out for me last time because I had it set to 5 and it didn't work. So thank you. In R, then, it has the packages that are needed. So if you just run this code as is, it will check to see if it's installed. If not, it will install it, and then it will load it for you. If you've already installed it, it will just load it, and it will go faster. Okay. So then we have general instructions about what you're supposed to do, followed by section-specific instructions as to what the model would contain. Note the troubleshooting help. The first 2 questions in each of these sections are designed to make sure that you are on the right track. So enter the model residual variance. That tells me that you have the right X and Y.
Yes.
Okay, if you get that right, you have the right ingredients in the model. Then enter the fixed intercept. As we just discussed in our formative assessment, that tells me if you have the right centering, if you have the right 0 point for your predictor. Otherwise, that number will be wrong. So if you put in Nintendo hours uncentered, you would enter 80. If I asked you to center Nintendo hours at 10, then you should have had 60, and that's how you would know that your predictor variables are set up correctly. In models with only 1 or 2 predictors, that's not a big deal, but once we get more complexity, then this will matter more. So for each of these, then, I would highly recommend completing the corresponding results section right after you find the numbers. Don't find all the numbers and then try to answer all the questions because you will get confused as to which model you're talking about. Now also note that I have bold 0 values here that show up. These are tied to the current status of your row in the database. So for instance, if I get the fixed intercept in here, I'll put a 70 in. I know that's not going to be right. I hit enter. So now the reference to the intercept down here is 70 because that's what I entered. So it's not the right answer, it's your answer. And the idea, okay, that's an important distinction. It's whatever the database thinks you have answered. And so the idea is that when I remind you, oh, the intercept is 70, what does 70 mean? And here are your choices. So the numbers should provide context as to what you should be talking about with respect to these choices. And some of these choices are generic, like this one is not data specific in terms of what a standard error means or what the intercept means. But the ones that have to do with making decisions, for instance, this one, significantly higher, significantly lower, non-significantly higher, non-significantly lower, those are tied to your individual data sets. So you may end up with a different answer than someone you're working with based on what's happening in your data. Okay? So they're roped together, yoked together. And these ones you do not get feedback on immediately. You do get feedback on the numbers immediately. At the bottom, it will tell you whether or not you have all your computational answers correct. When you do, it will say, good job. And you can celebrate with that. Okay, does that help clarify how this works? And in terms of talking about these drop-down answers, if you send me an email that says, I picked this one, is it correct? I can't answer that. But if you say, I picked this one and here's my logic, I can say your logic is correct or your logic is flawed and here's why. That may be a semantic distinction, but I think understanding the path to how you got to the answer is the important part. Because then that path can be reused as often as needed, algorithmically. Okay, I think that's all I wanted to say about that. And everything that you need to do this is part of example 2. So if you start with those source files, look for an example of what you're being asked and figure out what you need to change. It'll be the name of the data set, the name of the variables. As I said before, about 6 find and replaces will get you through this homework. It's meant to minimize the impact of coding because that's not the important part. If this is the first time you're using software, it can be very overwhelming. I want to make it as straightforward as possible. Once you get more comfortable with it, then we can start to add more things. Okay. Questions on any of that? We're good? Okay, we have a little bit of Unit 2 left to do then. Let me get rid of that. Hello, beach. That's a much nicer place to be. Do we want to go back through any of the example code or output? Are we feeling okay with that? What are we thinking?
I'm okay on the part of the binary code.
The binary predictor?
I know how to change or adjust, but I don't know the logic in why I changed this part.
Okay. So I think you're asking about the example with marital status as a binary predictor?
Yes.
Is that right?
Mm-hmm.
Okay, let me scroll to that. Scrolly. This page, this is page 7 of example 2, where we're at. So you understand what the code is doing, you don't understand why it's necessary?
Yes.
Okay, I can tell you that. Because the original version of this variable is coded 1 for unmarried and 2 for married. In that coding system, what would a value of 0 mean? The correct answer is, 0 is not possible. So then my fixed intercept would refer to a 0 value on this variable that is impossible. So to make it an interpretable intercept, we can subtract 1, creating a new version of the variable that I've named Mary01, and then the 0 group gets the fixed intercept. That would be the expected income for unmarried people. The slope would tell me how the married group differs from the unmarried group. The 1 group differs from the 0 group. So it's to get a meaningful intercept is the reason. Okay, and questions? I do not understand about the standardized estimate. Yeah, let's talk about that. That's actually a lovely segue because that's the part we haven't done yet, was return to the idea of correlation. So that is actually right above it. Standardized solution. The idea behind a standardized effect, which is like this beta right here, that number, that's a standardized slope. It is the result if you took both variables in the problem, education as the predictor, income as the outcome, and standardize them so that they have means of 0 and standard deviations of 1. That is what's known as a z-score. It strips off the differences between units. And so a standardized slope tells you how many standard deviations of a change you would have as a function of 1 standard deviation on the predictor. So as education goes up by 1 standard deviation, income goes up by 0.38 standard deviations. Now that I don't find typically very helpful. The reason that I would say this is important is because it's an index of effect size. It tells you on a unit-free metric of correlation how large the relationship is between these two variables. And the largest a correlation can be is either 1 if it's a positive relation, or -1 if it's a negative relationship. A relation of 0 means they're not related. Correlation of 0. So this is equivalent to the Pearson correlation between these two variables in this case. Okay, does that help? Maybe, yes. Okay, excellent. Other things that we can talk about or review in terms of how to do stuff or why to do stuff.
So I'm starting to cut it back from the beginning.
That's
So,
fine.
In the form of looking at the residual periods, in the command, the summarize command from the example, the y variable and then the x variable is correct, like one order outcome first, and then your
Oh, so are you talking about, so summarize in Stata? You're in
Yes,
Stata? Okay.
Stata, yeah.
Summarize is asking for descriptive statistics to be printed, so mean, variance, minimum, maximum, and that kind of stuff. These are not phrased in terms of being designated as predictors or outcomes, they're just straight variables.
Okay, so you don't have to worry about the order of
Nope.
that.
They'll just be the order in which they show up on your output. Where order matters in Stata and in R is on the regress command, because the first word after it is the outcome variable.
Okay.
Yep. And if you switch the order, then everything will be wrong in terms of your residual variance and your fixed intercept and everything, because then x and y have exchange places. And in R, that is the first thing after formula equals, your outcome variable goes there. And then your predictors go after the squiggle. Tilde. Okay. Other questions? All right. So this is one of the things that I was expecting folks to have familiarity with going into the class, Pearson correlations. If you don't, or it's been too long, like you had it but it's gone, that happens to the best of us, I just wanted to give you a few resources for that. I'm not going to ask you any of these questions on the homework per se. Pearson correlations you can get in bulk in a matrix form that has all the relationships across a series of variables. To do that in Stata, I use the command pwcore, pairwise correlation is what that means. That uses all possible data. So it does not delete cases that are missing any of the variables. It uses as much information for each correlation as you possibly can. So in this table, comma sig, can you guess what that is asking for? It's not sigma.
Significant digits.
Significance, yeah. So that adds this additional values right here. Those are p-values for your correlation. And I don't like that Stata does this. P is never ever 0. It's less than 0.0001 in this case. P can't be 0. So if I look at this, income and education are correlated 0.38. That is the standardized way of expressing the slope of how education predicts income. So I'd call that, I don't know, medium-ish in terms of effect size. I know that the best it can be is 1. But I can also get the correlation between binary marital status and income. That's 0.22. So that's another way of computing effect size. For variables that are predictors that are groups, though, R is usually not as helpful as D, a standardized mean difference. And that's the one that I have code earlier to show you how to get. And I can get how well the two predictors are related to each other. If you want to get confidence intervals for these correlations, you can do that by adding. So just like R has people who write packages and put them up so that other people can use them, Stata has this too. So Stata has what are known as addos.ado, which are like little programs that people make. And I found one called CI2 that makes confidence intervals for R. So you can install this and then run this code and it will print the correlation coefficient as well as the confidence interval for it, if you want to get those. In R, I downloaded a package called HMIS, which I think stands for miscellaneous, because the default version of correlation in R doesn't include p-values in a nice little matrix. So this one does. So the exact same table shows up here as correlations, and then the corresponding p-values show up in a separate table. And core test is a function that provides confidence intervals. So I asked for that using Pearson, 95% interval, and then that's the print out that I get out of that. So if you need to estimate correlations, here's how you can do so. Any questions on any of that? All right, then let's talk about ways to be wrong. Because we're making these decisions, right? This is significant. What if you're wrong? This is not significant. What if you're wrong? We haven't talked about that yet, but it's part of the story. Picking up on slide 54 in lecture 2. So decision errors and hypothesis testing, our last topic here. So if we're using a two-tailed hypothesis test, that means the alternative is not 0. We're not setting it to be positive or negative exclusively. We're allowing the possibility that we're wrong in both directions. Well, that means that no matter what decision we make, we have a chance to get it wrong. There's 2 possible ways this could go. There's 2 different kinds of errors. And I have them summarized here in the table. So first, if the HO is actually truth, if there really is no relationship between 2 variables and you're like, yes, there is 2, it was sufficiently unexpected, you could be making what is known as a type 1 error, or what is known more informally as a false alarm. There's nothing there, you thought you found something. How often is that going to happen? Up to you. That is the definition of alpha. How much percent of the distribution are you allocating to unexpected or significant? You can control that. If a false alarm is a really terrible thing and you don't want to alarm someone unnecessarily, should I put alpha higher or lower? Lower, right? I want to have the wrong answer less of the time. So conventional alpha of 5% means that in reality, for every 20 tests we do, if the null hypothesis is true, we're wrong once. We're wrong 5% of the time. If you wanted to be more conservative, maybe 0.01, you only want to be wrong once out of 100. More conservative than that, 0.001, like it's up to you. There is a push in some disciplines, like psychology, to remove the default 0.05 and make it lower to prevent replication failures and that kind of thing. So the 0.05, I think, is less of a given than it ever was before. But the other way to be wrong, what if you miss something? What if you say, nope, not significant, nothing to see here, and you're wrong? That's a type 2 error or a miss. Now here's the funny part. Can you guess what the accepted standard is for a type 2 error in the social sciences? You'd think it'd be 5%, right, to make them parallel? Nope. Any guesses? It's 20%.
I knew it.
It's 20. Because the other way that people talk about it is the inverse of a type 2 error. Not inverse isn't the right term. Opposite? Can I say that? Let's go with opposite. The opposite of a type 2 error is your power rate. Power is the probability of finding something if it's really there. Power is the probability of not missing. So we aim in planning studies to get enough people to have 80% power to detect an effect of interest. And that means we have to predict what that effect is. We'd have to decide that a priori. Not 0 is not good enough. We have to say, no, I want power to detect a correlation of 0.5 or a D mean difference of 1 standard deviation. We have to nail that down to anticipate power. So 80% power translates into 20% misses or type 2 errors. The other possibilities is you get it right. Nothing there and you don't find it. Something there and you find it. Now, when I first learned this, it was presented to me with distributions that looked like this, and I felt compelled to add one because everyone explains it this way. This slide makes absolutely no sense to me, and I made it. So can I give you a different version? That hurts my head less? Is that fair? Okay. I am going to play God. I'm going to make up a population where I know what's supposed to happen. Simulation. Believe it or not, this is how quantitative methodologists do their research. We make up data where we know what the right answer is, and we see how we get it back, and what factors matter in how accurately we get it back or how consistently we get it back. That's how we do methods research. So I made up data. 100,000 fake people. There is a true relationship between two variables of a correlation of 0.3. And then out of that population, the all y'all, I drew 1,000 samples of y'alls of 42 people, 63 people, or 85 people. And you might be like, that's awfully specific. Why did you pick those numbers? Wait for it. There's a reason. Here is the distribution of what that correlation ended up being across those 1,000 samples of different sizes. So 42 people each generates the right answer on average. So the 0.3 is right in the middle where it's supposed to be, as indicated by this line and my pink mouse. But there's a lot of variability. Some of the samples returned a negative correlation when the right answer is 0.3. Some of them returned a correlation as high as like 0.7 or so. What happens as we move from left to right? Gesture with me. Yeah. More people, more precision. We're less wrong on average. So R has a sampling distribution too, just like a slope does, just like an intercept does. It's a little trickier because it can't go past 1, so there has to be some adjustments to build confidence intervals that take that into account. But the premise, though, is R is more likely to be correct from any one sample the more people you have. Correct meaning what the population estimate is. So now we can talk about this in terms of power. How often would we conclude that there is a significant correlation in each of these samples? So I drew on here some benchmarks. Right here at the 2 is the goalpost, okay? The t-test statistic that you would have to cross to be declaring your correlation as significant. But because it's absolute value, there's 2 of them. There's a goalpost on the negative side, there's a goalpost on the positive side. The line in the middle is 0, the null hypothesis. So power is the percent of the time that you would be past the goalpost, in the right direction in this case. The rest of the trials that didn't make it past the goalpost are your type 2 errors. And if we look at the relative distribution of what is an error, meaning we would say it's not significant even though it's supposed to be, versus when we do find it, we do declare it significant, increases. Power increases as you get more people. So if I only have 42 people and the right answer is a correlation of 0.3, I'm only going to say that that's not 0 50% of the time. If the right answer is 0.3 and I have a sample of 63 people, I'm going to get the right answer that it is not 0 66% of the time. And if I go up to 85, it's almost 80% of the time. More people, more power. You are also more likely to find a significant result if you have a larger result to find. More effect size, more power. More people, more power. And they do interact. There's a nonlinear relationship. So this is one of the things that you would want to try to anticipate in planning a study. How many people do you need? I get that question a lot. You know what my answer is always? More. That's the correct answer. How many people do you need? More. Unless you're working with large secondary data sets of like hundreds of thousands of people, and then I would say maybe less. But most of us who are collecting data from real subjects who are difficult to find or expensive, we're under a limitation. So if power is 80%, that means our miss rate is 20%. Now, why these numbers? Some genius already figured this out. There are power tables, like this one from a classic textbook Jacob Cohen, yet again, in 1988. I found the whole book online, by the way. Here's a link to it. Yeah, I know. Apparently, if the book is old enough, they don't care if you steal it. But ask the Google, you'll find it right away. This table is actually from that book. I repurposed it in some of my teaching materials. The way to read this table is down the rows is the power proportion that you're seeking. What proportion of the time, if there is really an effect, are you going to find it? I have highlighted the row for 0.8 because that's the conventional goal that we are taught to strive for. Across the columns is R, ranging from 0.1 to 0.9. So the further to the right, the stronger your effect. These are only positive values of R. Do I need to make a table for negative ones? No. Power for an R of 0.5 is going to be the same as power for an R of minus 0.5. It's just which way the slope goes. The numbers inside the tables are the sample sizes needed to hit that level of power. And now you can see why I picked the numbers that I did. If my true R is 0.3, and I have a sample of 42 people, I'm only going to reject the null hypothesis that that R is not 0, 50% of the time. 63 people predicted to be 2/3 of the time. 85 people predicted to be 80% of the time. And damn if it didn't work. Like, it works. The maths. That's so nice to see. So where you would do with this in practice is, okay, I'm planning my dissertation. How many people do I need? Well, previous research in this area has indicated correlations around, say, 0.4. So to get 80% power, I need at least 46 people. That's called a power analysis. Lots of problems with that. Number one, how do you know what to find? Previous research suggests if you already know what's going to happen, why would you do the study? So there's not always some benchmark that's convenient and accurate that you can go off of. The other is, what if you're like, yeah, I can only afford 12 people? That happens for lots of reasons. So rather than approaching this from an a priori power analysis, what ends up happening in practice is what's known as a sensitivity analysis. And that's like, yeah, I got 12 people, what can I buy? What can I do with that? All right, so let's say I can afford 30 people. That means that if I'm targeting 80% power, that I have that if R is greater than or equal to 0.5. If I can afford 20 more people, now I have 80% power for an R greater than 0.4 instead. This is known as a minimum detectable effect size. And I think this way makes a lot more sense in practice to approach it from. Now, in our stories so far, there's only one R because there's only one predictor. Do you think you're going to do a dissertation with one predictor?
Yes.
Nope. Not going to happen. So then if you have two predictors, which R do you want? Or do you want the R for how well they work together? That's 3 different R's with 3 different sets of numbers. This is a fairly straightforward analysis. The rest of the classes I teach are filled with not straightforward analyses of various kinds, for which, honestly, power analysis, I just call it creative writing at some point, because you have to try to nail down so many specifics to make a prediction, and if any of those specifics are not right, the whole thing shifts around. But the concepts of how these things play together, I think, is important to have. The stronger your effect, the more likely you are to declare it significant. You have more power. The more people you have, the more power you have, no matter what your effect is. So if you look at this table, you can see that it's not linear. If I have a correlation of 0.9, I need 6 people to find it. If I have a correlation of 0.1, I need 783 people to find it with the same probability. And it gets even worse if you try to do better than 0.8. So if you go up to 0.95, for instance, to make it parallel with alpha, if alpha is 0.05, then type 2 errors would be 0.05, power is 0.95. That's 1,294 people. Yeah. So those of you working with large secondary data sets, does anybody have that problem? You have too much data? I've met folks with too much data. Like after you get 2,000 people, you're going to find everything. Everything's significant. So then nothing is significant, right? At some point, like you have to decide not based on p less than 0.05, but potentially based on effect size. If I'm overpowered, as they say, I might decide ahead of time, I'm not going to talk about anything that doesn't hit an effect size of at least 0.2. So how these things fit together again, just to remind you, type 1 and type 2 errors. Alpha is your type 1 error rate. Alpha is the probability of saying you found something when in reality there's nothing to find. Type 2 error is missing. There was something to find, but you missed it. The opposite of type 2 error is power. How often do you find the thing that's really there? How's that? Okay. What's next? I'll surprise myself. Oh, everything I just said, pretty much, but with one extra point. So in terms of what you have to worry about under which scenario, you don't have to worry about all the problems. If you declare something significant, meaning the t-value falls outside the critical boundaries, you're outside into unexpected territory, that means the probability of finding that if the null hypothesis is true is less than the definition of unexpected you set via alpha. Then by declaring your result significant, you reject the null hypothesis. You do have to worry about a false alarm. If you say, there is something here, I found it, you could be wrong. There could be nothing there. You don't technically have to worry about a type 2 error because you didn't say there's nothing there. You said there is something there. And that used to be the end of the story. But now folks are much more likely to be concerned about this because if you have very low power, you might have just gotten lucky. So if we go back to the table here for a second, if I have a sample, let's say, let's go back to the 0.3 column here. If I have a sample of 20 people and I find a significant correlation of 0.3, yay me! I get to publish that correlation. But you know what this means? I got lucky. I just got lucky. That would have only happened at a sample size of 20 about 25% of the time. So that means if someone tries to replicate my study, they have a 75% chance of not replicating it. I might have just gotten lucky. So you don't have to worry about type 2 error, but you still kind of need to pay attention to power because you could have just gotten lucky. The other situation is for a miss. So if t is inside the boundaries, in expected territory, your probability of finding that result is greater than the alpha level you set. I would say retain, because I'm out of room on the slide. Other people would say, do not reject. You can't say retain. Whatever. Just don't say accept the null. That's the one thing that we all agree on. You can't say that. But you can say it's non-significant. I don't have to worry about a type 1 error because I didn't say I found anything. I do have to worry about a type 2 error because I didn't find anything, and I could have missed it. Now, which is worse?
Depends what you're studying.
Exactly. The context completely matters here. So if I am trying to prevent another pandemic, and I want to make sure that I don't miss an outbreak, right? I might want to set unexpected to be pretty lenient, so I make sure I catch everything that could possibly start that pandemic. If I'm worried about unnecessarily scaring people, then I might go the other way. So I can't tell you which is more important. That depends on the context. But I can tell you there's 2 ways to screw this up and 2 ways to get it right, and that does not. Is that the end? Oh, we're almost to the end. Oh my gosh, we might actually finish Unit 2 today. That's exciting. For me, at least, I don't know. I got Unit 3 done, so I'm relieved about that. So here's our big picture summary. This class is about general linear models. That refers to a class of models that predict quantitative outcomes that are at least continue-ish. If you have other kinds of outcomes, come back in the spring and hang out with me then for 6270, the generalized linear modeling class. We'll talk about predicting binary things, ordinal things, nominal things, count things, skewed things, etc. General linear models are often called by different names based on what kind of predictor they have, but that's an artificial distinction. So we started with an empty model with no predictors. That's for pedagogical purposes. The idea is that if we have nothing predicting it, y and e give us the same information. E is how far off from the mean we are. So all of the residual variance of my e's would be all the variance in y as a starting point. If we add one predictor, generically written here, c is the centering constant in this. Beta 0 is my intercept, beta 1 is my slope. So for future reference in terms of the formative assessments, let's make 3 distinctions in terms of terminology: naming things, defining things, and interpreting things. So like for question 1, if I said, what's beta 0? Interpret it. It's the intercept. Now that's a name. The interpretation is it's the expected outcome value when your predictor is 0. And to further interpret it, you would need to have variables and units and things like that, like Nintendo and enthusiasm. That is based on a true story, by the way. My son does not like school because he can't bring his Nintendo there. He does have a Chromebook, by the way, and they play games on that, but that is insufficient. So he has a typical response: did you have a good day at school? No. Why? Because I had to go there. Okay, conditional on the fact that you have to go. Was it okay? I keep explaining to him, no, they will throw me in jail if you don't go to school. Like, it will become my problem. This is your job. You shall do it. And every morning I watch to make sure he actually walks in the door to the school. I don't just leave him at the playground, right? He's 9. I don't think he's figured out that he can skip school yet, but I don't want that to start without me knowing about it. So, enthusiasm does decline as a function of Nintendo usage. I'm going to tell you that. Beta 1 is a slope. That's the name. The interpretation, definition, is difference in y for a 1 unit difference in x. Slopes can be positive or negative. The problem with slopes, though, is that you got to know what the units are. And I like that a lot of you asked the question, well, what is a unit of enthusiasm? I didn't say. It's 1 degree on the feeling thermometer. I'm going to make some shit up. But yeah, that's the problem. Like if I tell you the slope is 4, you have no idea if that's a lot or not until I tell you what the variables are and how they're measured. That's the reason why we need effect sizes to go with the slopes, because those standardize them into some kind of unit that has inherent meaning. Difference between 0 and 1, for instance, as a correlation. E is how wrong you are. Residual, or error. It is how far off your actual y is from what's predicted. So if you're higher than predicted, your E is positive. If you're lower than predicted, your E is negative. E's always have a mean of 0. And because the intercept is tied to when your predictor is 0, that's why I recommend centering it so that 0 means something. In the Nintendo example, 0 hours of Nintendo is possible. There are some children that do not play Nintendo. They probably don't have one, and that's why they don't play, and they want to come to my son's house to play with him, just like my little brother did to his friends when he was little. Those times have not changed. Now it's Nintendo Switch as opposed to the Nintendo box with the cartridges, but it's the same idea. But if the sample did not have anyone who doesn't play Nintendo, then setting a reference baseline, I like that word too, of 0 is not helpful, because there's nobody in the sample that looks like that. So the intercept is the you are here sign of the map of your data. You want it to be in the data somewhere, not on the periphery or in some other airport. Okay, how are we doing? You got energy for one more slide so we can finish this?
Yes.
We got it. All right. Foreshadowing. So in a GLM with a single predictor, this unit used a quantitative example and a binary one. The effect size is given by Pearson correlation. And if you're feeling ripped off, I don't blame you. 58 slides later, I reintroduced Pearson correlation by a whole nother naming system. Now the real utility is in expanding the model. So there's a lot of instances in which you might want to do this. In the next unit, we will look at how to examine nominal or ordinal predictors. Those are categorical variables that have 3 or more levels. We can't stick a slope in for them and have that work. It won't mean anything. If I say 1 is cat, 2 is dog, and 3 is rabbit, drawing a line through that as if they're numbers doesn't make sense. We're going to have to recast them in a series of binary variables instead. That's going to take more than one slope. We also might want to examine nonlinear slopes of quantitative predictors. Do you think there is a relationship between Nintendo and enthusiasm for school that keeps going forever and ever? This way. Like, as you play Nintendo for 24 hours a day, your enthusiasm continues to decline at that same rate? I don't know. That seems unlikely. What is the relationship between like money and happiness? Does money buy you happiness? To a point, exactly, right? Like if you don't have money, it's hard to be happy because you're too busy putting out all the fires that you have to deal with that money could put out for you. So yeah, up to a point, money and happiness may have a relationship, but once you have your needs met, is being super rich make you happier than someone who's doing okay? It levels off. Or there are trends that go up and then come back down, like the arousal performance curve, right? You don't care or you care too much, that's bad. The sweet spot is kind of in the middle. So if you have any of those kinds of relationships that you want to examine, that straight line is insufficient. A Pearson correlation is the same thing as saying it's a straight line. It's insufficient. We can't turn Pearson correlation into anything but what it is, but we can turn our model into whatever we want. So that's coming next. In that unit, we're still dealing conceptually with just one predictor. But research questions often have lots of predictors involved. Or you want to know if 2 things are still related after you factor in a common influence of a 3rd thing. There's a lot of research questions that are phrased that way. So then we get to talk about unique effects. That is related to things like semi-partial correlation and partial correlation. We'll get into a little bit of that with respect to effect size, but not in terms of correlation straight away. And then last but not least, the last unit is interaction terms. That is the idea of moderation. Do you think the relationship between Nintendo usage and enthusiasm varies by child's age? Does it vary by their background characteristics, like their home situation, how many Nintendo games they have? What? Gender, there's another one, gender identity, yeah. Do these relationships hold for everyone, or do we need to say, well, it kind of depends on this if we see this happen? Is stress bad for you? She's looking at me like, are you kidding me? Is it as bad for you as it is for me? Could it be that people who have better coping skills are less bothered by stress? Or people who exercise more or have better physical health? If the relationships are conditional, if it's like, well, it kind of depends, that's a moderation research question, and that's answerable by literally multiplying the 2 variables together and seeing what happens. This is my favorite thing to teach of all the things I do. I'm looking forward to that unit very much. But we got a couple months before we get there. But that's where we're headed. All of the things on this slide you can't do with just a Pearson's correlation. That's the entry point. Ta-da! We did it. I know, I'm happy. Any questions for me at the moment? All right, then here's what can happen. You can put off doing writing by working on your homework assignment. That is due next Wednesday. The TAs and I are happy to help. You can stop by office hours and chat with us or send us emails. Try not to work on anything for more than 15 minutes. If you get stuck, ask for help, please. Okay? All right. See you Thursday. Thanks for being here, everybody. Bye, Zoomers. Bye, Roomers.